Hi, I'm Todd Austin. I'm a professor at University of Michigan and also co-founder of Vegeta Labs, which is a startup that makes the TrustForge secure computation platform for Amazon, AWS, and Microsoft Azure. And today in this video, I'm going to do a programming tutorial for TrustForge. Let's get started. So Vegeta Labs is a startup in Ann Arbor, and it makes this TrustForge product, which has been deployed on Azure and AWS, and it's essentially a next-gen security and privacy platform. And it provides two capabilities to the cloud platform. The first is called encrypted computation, which is the ability for the Xeons in the cloud to perform instruction-level operations on encrypted data without software having the ability to decrypt that data or having keys to access that data. This allows you to provide a computational service over your own data or third-party data without having the ability to see that data. That can prevent data breaches. It can also provide privacy-enhanced programming capabilities because I can ensure my clients that I can't see certain aspects of the data they're sharing with me. It also provides a capability called safe data release, where a data owner and a TrustForge user can agree on a piece of code that can compute over the encrypted data of the data owner, and the results, only the results of that code can be decrypted and revealed to the TrustForge user. That can allow you to do safe data sharing, like here's my genomics data, you can run machine learning and you can see the weights over that data, but you can't see anything else about my data. So it's a very flexible programming framework, and it's deployed as a programming SDK in the cloud, and it's on Microsoft Azure and Amazon AWS currently. You can use it on both those platforms. Programmers get access to these programming capabilities by programming in C++, JavaScript, or Python. And the system's been integrated with leading database and web UIs as well. We're working with our partners to do world-class security validation of this target. Over the past 2 years, we've been commercially red teamed, as well as undergone significant formal verification of the TrustForge platform and its hardware enclave. And over those 2 years, we've revealed no vulnerabilities in the platform. So this really is incredibly powerful security technology that's appropriate for use as a privacy-enhanced programming system. And then this video and then the other videos in this series really demonstrate the diversity of applications that can be tackled by the TrustForge platform, ranging from medical applications to advertising, fintech, surveillance applications. We even have a video that shows you how to detect if two spy satellites are going to hit each other. It's really the Swiss Army knife of privacy-oriented programming. All right, let's take a look inside the zone of trust of TrustForge. TrustForge is a tiny little hardware enclave that we've deployed into Azure and AWS. And it exports a public key that third parties can use to allow the TrustForge enclave to access the data that they've supplied to the main system in encrypted form. The software and hardware of the main system cannot access that data because it doesn't have access to the decrypted data, and it doesn't have access to the keys to access that data. The only entity in the system that can access that data is the TrustForge enclave. The TrustForge enclave is accessing and computing directly on that data with these RISC-like instructions, and it's doing it in a way that eliminates software vulnerabilities and any side channels that could get access to that data. In fact, you can hack any of the software in the system. You can change any of the software in the system, and you cannot see what the data is that's being computed on by the TrustForge enclave. In addition, you can hack any of the hardware on the main system, and it cannot see the data that is being operated on. All you can do is steal and manipulate encrypted data. And then we've designed the TrustForge enclave to really be resistant to any form of software attacks or hardware hacking by eliminating what are called side channels in this hardware. It's really next-gen hardware that's been both formally verified and red teamed as well. Anything that travels outside the TrustForge enclave is encrypted all the time under a strong cipher and contains all the information embedded within that encrypted packet. And we can tell if that encrypted packet has been manipulated in any way. So it's a really powerful technology, as we'll see in the programming demo today. Programming the TrustForge enclave is pretty straightforward. Basically, all you have to do is decide what variables in my program do I want to protect, and I just declare those as TrustForge variables. So essentially, integers, which were ints and unsigned ints, become TrustForge ints and TrustForge unsigned ints. These encrypted variables are bit-for-bit compatible in terms of their semantics as the unencrypted variables, but they're encrypted. And they're about twice as large in their encrypted form than they are in their unencrypted form. On average, about twice as large. And we support on TrustForge integer variables of any precision that is normally supported by the Xeons of the cloud, as well as floating point, single and double precision, as well as Boolean, as well as character and string variables as well. And then the SDK comes with a full range of string libraries, as well as math libraries as well. So you can do sines and cosines, arctans, and string concatenates, etc. This can all be done on these encrypted variables. Now, there's two things you cannot do inside of TrustForge programming, and these are essentially bad programming practices. One is TrustForge encrypted variable cannot influence a branch in the program. So if statements on encrypted variables are not possible. So the way you do decision processing in TrustForge programs is you have to use what's called a conditional move primitive. And we'll see that in the demo today, but it basically takes a predicate and then the true and the false value, and then assigns the correct value to that. It's using a technology from compilers called predication. It's pretty easy to convert a program to use this, and we're actually at the startup developing technologies to do this automatically, but it's really not very difficult to do. The second thing you can't do with a TrustForge secret variable is you can't create a pointer from it, because then you could look at the memory accessing from that pointer and you could infer information about that encrypted variable. So in order to do a secret dependent memory access, you need to use what's called an oblivious RAM primitive, and I'll demonstrate that today in the demo, the oblivious RAM primitive. So we'll see both these restrictions, and these are not restrictions that TrustForge imposes on you. These are restrictions that secure computation imposes on you. So if you violate either of these two situations, then it's very easy for an attacker to figure out what your secrets in your program are by looking at the control flow of your program in this case, or looking at how you access memory, data memory in this case. So TrustForge is fail-safe in that, and we'll see this in the demo today, in that if you do either of these operations, you don't get a vulnerable program. You just don't get a program. It says, I cannot do this operation. So it's actually pretty easy to follow these rules. The compiler will tell you when things have gone sideways and you need to fix something. So it's really easy to program in this environment. I love programming in this environment. And I'll just say that, in the marketplace, TrustForge Secure Computation Platform, it primarily competes against two other technologies, which are homomorphic encryption plus zero-knowledge proofs, as well as multi-party computation plus zero-knowledge proofs. And if you've had an opportunity to program in homomorphic encryption or zero-knowledge proofs, you'll know, for me, it's like a punch in the face. It is absolutely brutally hard to program in these systems because as you use data, it decays. There are only linear operations. Zero-knowledge proofs are completely bespoke for whatever application you're doing. And TrustForge really departs from that by allowing you to use the variables you always use with the operations you always use. It limits you in some ways because we don't want to be able to infer information by how the program operates, but it does that in a way where you don't have to be absolutely correct in how you build your program. It'll tell you if you did something wrong. And then releasing information doesn't require these bespoke zero-knowledge proofs. It just requires that you agree with your data owners on what code can release data. It's so much easier to use than these other technologies, and frankly, I love programming in it. That said, I'm a huge fan of zero knowledge proofs and homomorphic encryption because they've really shined a light on what kind of practices can improve privacy-oriented programming. All right, so let's now jump into the TrustForge programming tutorial and see how we can develop a program that's initially not privacy-oriented, decide what parts of that program, it doesn't have to be all, it can just be what part of that program we're going to privatize, and then push that till it's actually a privatized program. And I'll walk you through all that. All right, here we are, ready for some demos. In this demo, I'm going to build a privacy-oriented program. I'm building it from an existing program. I've got two windows here. The top window is my edit window, and so I'm going to start editing my program. C++, it is a LeetCode medium result that I've done, which is basically in this application, I'm going to read a number up to 64 bits, and then I'm going to call two functions, pop count, which is going to count the number of ones in number, and then isEven is going to tell me whether or not the number is even or odd. And then it's going to print the number of ones in the value, and then it's going to tell me whether it's even or odd. Okay, so it's a very simple little application, and we can take a look. And then, by the way, I'm running on Linux here. I have TrustForge running on Linux, and let's take a look at my two functions. So here's my popcount function. So count gets 0 while value is non-zero. I'm going to convert the 8 lower bits of value to a count, and then I'm going to rotate down 8 bits. So I'm going to basically do it in 8-bit chunks. And then you can see I've got this val to pop table, and basically what this does is I index this table, and it tells me the number of ones in the index for the table. So it starts out as 0, and it goes all the way up to FF, where the count is 8. There's 8 ones in FF. There's 7 ones in FE. There's 7 ones in FD. There's 6 ones in FC. Okay, so this is kind of a great time-space trade-off. I'm trying to impress my LeetCode medium co-developers. And so then I iterate on this until the value is 0. If the upper bits are 0, I don't really need to add any more. So as soon as the value of value is 0, I don't need to count anymore because I know all those bits are 0. And so then I return the count at that point. And then isEven just takes the value, and it looks at the least significant bit, because in 2's complement, the least significant bit tells you if it's even or odd. And if the least significant bit is a 1, then it's odd, so I return false because it's not even. And if the least significant bit is 0, then I return true because it's even. All right, so, and then I come down here and I just say, make clean build, and I make my application, and I run my TF demo, and I give it a number, 42, 43. And we see 43 there's 3 bits in B and 1 bit in 2, so a total of 4 bits, and 43 is false. It's not even. So, hey, that worked out pretty good. All right, now let's talk about privatizing this application. Essentially what I want to privatize is what the number is. Okay, so the user's going to enter a number, and then I'm going to encrypt that number. And then what I'm going to do is I'm going to call these functions. I'm going to convert these functions into a privatized version of these functions. So they're going to operate on encrypted data. And we're going to see that this is actually a super inefficient way to operate on encrypted data. So we're going to make some changes in that function as we go forward to try and improve its performance. And I'll show you that process. And then, we got an if statement here. We're going to have to deal with that in this function. So there's a lot of interesting stuff that's happening here that we're going to have to deal with. And then we're going to get encrypted value of ones and encrypted value of even. But then the problem is I'm going to have to somehow decrypt these values. So how do I decrypt those values? We're going to use what's called a datagram. So let's get started on this programming problem. So first, the preliminaries. What I'm going to do is I'm going to come up here. I'm going to add some information at the top. I'm going to add my TrustForge interfaces. So I'm just going to include TrustForge.h. I'm copying from another file off to the side here where I've got everything working. And I'm also going to add some other data that we're going to see later. This is the data for data grants. We'll see this information a little bit, but I'm going to copy it in here right now because we're going to need it later. This is information that will allow me to eventually get access to, get access to that data down below. Okay, then I'm going to come down here and I'm going to do one other preliminary thing. When the system starts, I'm going to initialize my TrustForge engine by just calling the TrustForge initialization. Okay. Now this takes what's called a contract. So I can pass a file name to a contract. That's my permission to access this data, and I can also give access to what's called a debug contract, so a decrypted contract. And that'll allow me to decrypt the data as well. We'll look at that in a little bit. But basically, I'm just going to put those on the command line using environment variables, so I don't have to update those. All right. So now, as a programmer, I'm going to decide, like, what do I want to make privatized here? And what I'm going to privatize is I want to convert this number to, TF int TF long 64. So I'm going to convert that to a TrustForge encrypted variable, 64 bits. So which is comparable. And I want to make that a ulong as well. So that's an unsigned long, 64 bits. So that's the uint underscore t variable as an encrypted variable. And then I'm going to assign to it this unencrypted value. So what's interesting in TrustForge, you can always take an unencrypted variable and make it encrypted. That's certainly possible because programs have constants in them, so you need to be able to mix those constants in. What you can't do is take an encrypted variable and make it decrypted. That's not possible without a data grant. Also, what's interesting about this program is it's reading the input here and then it's encrypting the variable here, and that's just because we're doing a demo. In a real program, typically this information would be read by a client in JavaScript. So we have a JavaScript client library that you can use to do that. And then it would import the data into the program in its encrypted form. I'm not going to do that here just because I need a more standalone representation. We're not going to use React. It's just going to make it too complicated. So we're just going to read the program and we're going to encrypt it. When we encrypt it, we're actually going to use an instantiation of an encryption. And we're going to, since it's coming from the outside world, we're actually going to indicate what the type of that variable is. So let me show you this as well. So this is an instantiation. This is actually a client-side operation. I'm doing this in the program just as a demo. I'm indicating what the type is and what its value is. The reason why I indicate what the type is later we'll see the integrity checking mechanism will want to ensure that we used a specific type of, a specific class of variable that were inputs to the computation. So I'll indicate that here. Then I come down here and, these also are going to be encrypted variables. And what's interesting is if number's encrypted and number goes into pop count and number goes, then whatever comes out of pop count has to be encrypted if it's a function of number, which, typically it's going to be. So now I need to encrypt these variables as well. So I'm going to use the TrustForge comparable variables here. This is a TF int 32, and this is a TF bool. Okay, now these are all encrypted. All right, and then I can just come down here and I can say, let's compile our program here. And then you'll see that it'll say, hey, this function pop count doesn't take an encrypted value, so you're now going to have to go up here, and you're going to have to get pop count to take an encrypted value. So let's get pop count to take an encrypted value. Okay, so we want to take a TF long 64. That's a 64-bit unsigned. And then, okay, great. So we fixed that problem. And this is typically how I program, by the way. I just let the compiler tell me what to do next. And then I come over here and I say, what did I do now? Look at this. It says, hey, dude, you cannot use an encrypted variable on a while loop. This goes back to that earlier point I made that you cannot influence the control flow of the program with an encrypted variable. So now I have to think, I go, oh man, this is a mess here. What do I do? I have this check of value here is just saying, is the upper bits equal to 0? I certainly don't want an early exit if my upper bits are equal to 0, because then I can tell how big the number is by looking at how long pop count runs, right? So the TrustForge compiler is not at all going to let me do this. So what I have to do is I have to come up with a version of my program which does the same computation, but is fixed in terms of how many iterations it has in its loops. And, so obviously what I need here is I need the ability to run this loop a total of 8 times, right? So each time I run this loop, I chew off 8 bits. It's a 64-bit value. So what this loop is really doing is it's doing up to 8 iterations. So for my privatized program, I'm just gonna change this to a while loop that executes 8 iterations. Right, and that's fine. I'll do a little bit more work when it's a small variable, but I won't reveal in the program that this small variable is small. It'll always do 8 iterations. Fantastic. So I've solved that problem. Now let's come back down here, and we'll build the program again and see what happens. Still problems. Let's see. So now it's telling me, there's no way to index val to pop with a secret variable. That was the other rule I talked about earlier. Here I'm trying to take a secret variable and index into memory through this val to pop array. That is not possible. Why is that not possible? Because if I were to do that, then I could look at what memory was accessed, and that would reveal information about the lower bits of value. This is the classic prime plus probe or Spectre meltdown attacks that use this capability. TrustForge just doesn't even allow it. So we're gonna have to use what's called an ORAM primitive. So let's just move in an ORAM primitive here. And so I'm going to replace the kernel of this function with a little bit of code here. So these lines here, I'll highlight them, and I'll go through each of these lines, are going to replace this line right here. Okay, so come down here, I'm going to delete this line. Now, let's just see what this particular set of lines do. The first thing we're going to do is we're going to get that lower 8 bits of value, right? Because we want to index this table with the lower 8 bits and convert it. All right. And then the value I'm going to read from the table, I'm going to set that to 0. Then I'm going to walk the entire table, 256 entries. I'm going to see this is a bad decision from a performance standpoint, but we're going to fix it later. And then as I'm going through the table, I'm going to use this conditional move primitive. This conditional move takes an encrypted predicate. It's saying, is the index that I'm currently at, that I currently want to read, which is lower 8 bits of value, equal to the index that I'm iterating on? If it is, I want to return the entry in the array at index j. Otherwise, I just snatch the value over again. This is called an oblivious RAM scanning primitive, and it allows you to access memory with a data-dependent index in a way that nobody can tell which entry you accessed, because I accessed every single entry and I wrote every single entry at the end. And then, by the way, what's interesting about the cmove primitive is you can't tell if I put val into val or if I put int32 val to pop into val, because the crypto used in this framework is what's called semantically secure. So there's no correlation between the data we're encrypting and the ciphertext that's used to represent it. I'll show that when we actually get this program running. I'll show you how that works. It's pretty cool. So you can't look at the output of this line of code and know which one of these I chose. If you could then figure out this predicate, and you could then know something about this index, and that's a problem. So you cannot. All right, and then I take this val, which is encrypted, and I add it to count. Oh, now count's not encrypted, so I'm going to have to encrypt count too. All right. And let's see, I'm going to get the encrypted value of count is TF in 32. Yep. And then down here, oh, I'm going to take value and I'm going to shift that by 8. That's fine, no problem. That's an encrypted value. And then after I've done 8 iterations, I'm going to return the value of count. I think this is right. Let's just give it a shot here and see what happens. Warning. Oh, no guard. Yeah, I'm an idiot. I need to open brace this loop here. Okay. And compiling one more time. And I come up here. Oh, check it out. Now we're at 288. Are we past this function? No, it says cannot convert. Oh, look what's wrong here now. See how the compiler just walks you through the conversions you got to make. It's so cool. Yeah, I can't convert count, which is encrypted, to an integer. That's decryption. That's not permitted in this system without a data grant. So the compiler just says, dude, you gotta change that to an encrypted variable, or we're not going to build this program. And that's interesting. That really goes to what TrustForge does, in that it's fail-safe in its ability to build programs. And that if you make a mistake, like I returned this encrypted value as decrypted, now I've exposed this value to the whole world, they're just not permitted. And so you'll see as we're going through this development, the compiler is simply not permitting it. And that's not because the compiler is really good. It's because there are no operations to do these things. The hardware cannot do that. And so the compiler doesn't even know what to do for you. There's no way to express this particular computation. It's a really awesome system from my perspective. I really like programming in it. So I'm going to change this to TF int 32 as well. Now we've got encrypted variables on the output. Let's take one more try here and see if we got to the next function. Okay, we're now down to 319. Awesome. Now we've got pop count is returning an encrypted value. Now we got to do is even here. Okay. So is even. So let's just, right away, that's got to return a TF bool, right? Because it's getting a TF u long 64 value. It's encrypted. Okay, good. Let's see if that works. Of course it's not, right? Spoiler alert, can't do an if statement on a secret variable. It says, sorry, but there's no way to, do an if on this value. Okay. So now what I need to do here is I need to convert this to what's called predication. So now I'm going to predicate this. And I'm going to just cut a bit of code over here. Master program. Okay. And let's see here. And so this code I'm going to replace with this code. So first thing I do is I just compute the predicate, right? The predicate is the lower bit 0 or 1. So and the predicate is basically, is it odd? And then I'm going to define the return value, and the return value is going to be false if it's odd, or true if it's even. And this operation doesn't reveal anything about whether it was true or false. Retval gets us a random ciphertext every single time, and then we just return retval. So now we've converted this if statement using what's called predication. It's not a new idea, it's an old idea, but it works great in the context of trying to eliminate control flow dependencies from secrets. And so now we're just going to delete this code that we replaced. Now we've got a function that returns an encrypted value that's true when it's even, and returns an encrypted value false when it's odd. Okay, let's give it a shot, see what the compiler says here. Okay, oh, look at this. Oh my gosh, 320. Yay! Even is working. Okay, now, here's the problem. Yeah, it says you can't print this value out. Ugh, that's a mess. Why can't you print this value out? This value is encrypted. You don't even have access to this value. And so what we need to do now is we need to get permission from the data owner to get access to the value ones and is even. In fact, actually, I already have this number, so I'll just change this one to input. Let me rebuild one more time down here. And here you see ones don't have it, even don't have it. There's no way to print these values because these values are completely random. They're just ciphertext, and I don't have the ability to convert them to in this case, a Boolean, because I want to print out true or false, and in this case, to an integer. I don't have any way to convert encrypted ones to an integer value. Now, the way I get that ability is I get that ability through the use of what's called a datagram. So what I'm going to do is I'm going to add just a little bit of code here. I'm going to define two additional variables here. One's decrypted and even decrypted. Now, these are no longer encrypted values. These are back to their integer values and their Boolean values. Okay, but I need to be able to decrypt them. And I'm going to use what's called the safe data release mechanism from TrustForge. And the safe data release mechanism for TrustForge is built around this structure called a data grant. Okay, so I have two data grants. I have the ones data grant and the even data grant, which is going to print out the values if I do the computation that we agreed upon. All right. And then if those data grant values do not function correctly, then it's going to print an error that says I do not have the ability to decrypt these values. All right, so let's get started here. First, we need to instantiate the data grants. Oh, and then down here, I want to convert these two. I want to convert these two variables to the decrypted version. Okay, and then the last thing I need to do is I need to instantiate the data grants. I need to load in the data grants. And essentially what a data grant is it's a hash of the data flow graph used to compute this value of ones and even encrypted under the same key as the data. So it actually comes to us from the third party user. All right. And then once I have that data grant built, and so I have a ones data grant, and then there's an ID for the data grant as well as its decryption value. Once I have that data grant in place, and then in the background, what I did is I built these data grants for this version of the program. So we'll be able to execute these data grants in this program. But let's save that. And okay, we're back. It took a moment just to get my data grants in order, and so they are. And so now I'm going to build this program. And it builds no problem now. Everything seems in order. And now I'm going to run it, and I'm going to just specify in the command line here what the contract is. When I run the TrustForge program, it's going to open up the data contract to get access to the encrypted data. It's going to read my input, and it's going to run, and it's going to successfully decrypt those values. So it says 43, the value is the hex value, has 4 1 bits, so that's 3 for the B here and 1 for the 2, so a total of 4. And the number is false. I can run this again, give it a big number. Fantastic. And it'll do all those counts. So 19 is like 3 plus 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Hey, perfect. And the value is true because that's at a 4. Fantastic. That worked great. Now I want to show you how inefficient this particular algorithm is because it does this scanning, this oblivious RAM scanning of that val to pop array. So we're going to actually change that function. But in order to motivate that better, I'm going to use a little tool that I use when I program called stopwatch. So what I'm going to do is I'm just going to open up a context here of stopwatch. And this is just a class that is going to count cycles during the execution of this scope. So specifically, I want to find out like how long does it take to do these two operations in encrypted form. So I'm gonna write that out. I'm gonna come down here. I'm gonna build my program, and then I'm gonna run again. Put in my 43. Okay, and then stopwatch says, okay, so to compute this pop count and is even, it took a total of 13 million processor cycles. Okay, now this is pretty inefficient because of this oblivious RAM data access. So what I really want to do here, I want to be a little bit smarter about how I do pop count. And this may seem somewhat counterintuitive, but what I need is the best data oblivious algorithm that I can get for this. And what's interesting is it's probably the most simple algorithm. So I'm going to replace pop count with just a simple bit counter, 64-bit bit counter. I'll copy that in here. So if you're doing elite code programming, this is probably the one you started out with. And it turns out in encrypted mode, this is actually pretty efficient because it's less data heuristic. So in this particular algorithm, I'm gonna count each of the 64 bits. I'm gonna look if the lower bit is 0 or 1. I'm going to convert that to an integer and add that to count, and then I'm going to shift right by 1. Now, I won't end early because, if the value is 0, I can't know that. So I have to do 64 bits. Why? Because it's a 64-bit value. But this is a fairly efficient program in data oblivious fashion because I don't have to do all the scanning of these arrays. So let's do this, but we need to do one more thing. We've actually changed the code here, so we need to change our data grant. So I have a second data grant for the ones function here, which is the optimized version of it. So now let's build our program. And then let's run it again. And then let's note, so we had 13 million cycles here. We'll give it the same input, 43. And look at this. That function is only 40,000. It's significantly more efficient. And that is what's interesting about data oblivious programming that is independent of the program's data, which has to be the case when your data is encrypted because you can't even look at your data. Sometimes the algorithmic decisions you make are somewhat counterintuitive. All right, and this program, it'll run mostly the same amount of time for any input because it is data oblivious. So there's small variations because there can be interrupts and such. This is just raw processor cycles I'm monitoring here. But for most of the different executions of this program, it's going to be roughly the same number of cycles because it is data oblivious. Now I want to show you one other really cool thing about this application. Let's say we come in here and we try to do a supply chain attack. I want to get your I'm always going to make your pop count one less than it really is. Or maybe let's make it one more than it really is. So I'm going to add one to pop count. And then I come down here and I build the program again. And what's interesting, in encrypted computation, you can do any computation you want. You can just never see the results unless you have a data grant. But the data grants are linked to specific versions of the program, specific data flow graphs to compute a value. So when we run this program, which tries to add one to pop count, it says, sorry, I can't do that because your data grant doesn't match. In fact, there's nothing I can do here until I undo that change, produce the original stream of computation that I had created in the beginning, rebuild the program, and then execute that program as its original program. And then it'll allow the release information. What's really cool about these data grants is now you have the ability to agree with your clients about what code you can run on their data. And as long as that code doesn't change, either by hacking, either by a rogue programmer on your team, either by supply chain attacks, somebody underneath you changed something, if none of that happens, then the data grant works. If any changes in the program, any subtle changes in the program occur, then the data cannot be released. So it's a really powerful mechanism. And then just the other point about encrypted computation, you've got integers, high precision integers, floating point. You've got all these capabilities available to you. It's really, from a privacy-oriented programming standpoint, it's really the most capable framework that exists today. I want to do one more thing before we end this demo. I want to just print out what is the information that is being encrypted or is being processed by the PopCount program. So what I'm going to do is I'm going to print out every time I run this program as count is updated. I'm going to print out the value of count. Let's see, encrypted count. Oops, sorry. And this is just a little pattern I use for basically it takes the 128-bit value that count becomes. This is roughly 4 times as big in this case, but and it's just going to print the actual raw data associated with count. And this shouldn't blow the data grant because we haven't modified any of the computation. Okay, so let's build our program. And let's run our program. I'm going to put in 43, and you can see the value. This is the information that's being computed on, and you can see it's just random, right? It's interestingly random, and it is what's called semantically secure. So that means that if you do any computation on the data, you get a new random value, and so it's really interesting. Let's just take a quick. Just going to copy these into here. Let's look at the tail end of this output. And then what we're going to do is we're just going to run this program again and give it that value 43 again. And then look what happens here. Look at this. Look at the values are completely different again. And the reason why that is because the enclave is injecting what's called true random noise into the computation. It's not affecting the values that you're computing. Those are bit for bit maintained. But we inject into that packet what's called salt. And so you can just keep running this over and over and over again on the same exact inputs. And you will never see the same information spitted out in that encrypted count value ever again. That's called semantic security. What that does is it prevents anybody from analyzing the data in your system to try and infer what is happening with that data. It's a really powerful capability, one that TrustForge just has, really down. And in fact, when we went into red teaming, the first thing the red team did is try to analyze our ciphertext, and it's very high entropy. There's about 62 bits of entropy in that ciphertext. Really incredible, incredibly hard to understand what's going on by just looking at the ciphertext. Okay, that's the end of my demo. I'll include this application in the VIP bench, so if you want to grab the source code, just go grab the VIP bench, which is on the slide that I'll show you in just a moment. But thank you for coming to my demo. All right, I hope you liked that tutorial. It was a lot of fun to make it. It was a lot of fun to program it. I really enjoy programming in TrustForge. It's really exciting to be able to use these technologies to, enhance the privacy of applications and do it in a way where you don't have to be a cryptographer to figure out what's going on. So thanks for coming along for this tutorial. If you want to learn more about me in particular, you can go to my LinkedIn page at this address. And then if you want to see more examples of privacy enhanced programming that works on the TrustForge platform, go check out the VIP bench benchmarks. These are a number of privacy enhanced applications that have been co-developed by Ajita Labs, University of Michigan, Addis Ababa Institute of Technology, and New York University. So you can see there's about, I think, 45 programs in the benchmark suite today. So it's just a great place to see different kinds of privacy-oriented programming applications. And if you want to learn more about TrustForge and see if it might be able to solve some privacy-oriented programming practices that you want to implement in your DevOps, just drop me a note or come to ajitalabs.com and learn more. It's really easy to get access to the demo for TrustForge and really easy to spin it up on Azure or AWS. Thanks so much for watching the tutorial, and take care.